Okay, ladies, so today we're going to learn about Newton's second law. Newton's second law. The acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. So what does that mean simply? F equals ma. This one's a really important one, so take a moment to get out your formula sheet to write this down. So we have our net force equals the mass of the object times the acceleration of the object. And you'll notice it's a sigma F. So again, from yesterday, remember that sigma F means the vector sum of all external forces acting on the object. So we're taking a look at all the forces, and we're just talking about the net force is the mass of the object times the acceleration of the object.
Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there. But this one is heavier, and you're going to have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm going to do is I'm going to try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm going to put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and... Could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of if that price of fuel keeps increasing. We want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. MacMillan Space Center, I'm Cam Cronin. Thanks again, Parnelli.
Here's example 1. Space shuttle astronauts experience acceleration of about 35 meters per second squared during takeoff. What force does a 75-kilogram astronaut experience during an acceleration of this magnitude? Now, why don't you take a second and write your givens? I'll give you a little bit of time. Okay, so let's take a look at our givens. So we have our acceleration equals 35 meters per second squared. And if I'm thinking about the little shuttle here, we have the acceleration going up because the shuttle is actually going up. So we're talking about a positive acceleration. And we have a mass of 75 kilograms. Okay, so what are we trying to find? We are trying to find our force. So the equation that we're going to use is F equals ma. When we solve this, it's going to be force equals mass, 75 kilograms, times acceleration, again in a positive direction, 35 meters per second squared. And when I get out my calculator and I do that, I end up with 2,625 newtons. But because there's two sig figs, I'm going to go 2,600 newtons. So this would be the force experienced in an acceleration. And then we are talking about in an upward direction, since it's taking off. Example number 2. An 8.5 kilogram bowling ball is dropped from the top of a super high mountain. As the ball speeds up, its speed reaches terminal velocity. Terminal velocity, by the way, would be when it can't go any faster. That's the maximum speed something can hit during free fall. So the first sort of statement is, what's the sum of the forces on the ball when it is first dropped? And then what's the sum of the forces on the ball when its speed stops increasing, aka it reaches terminal velocity? What force is acting to slow down the ball? Again, I'll give you a second to draw some force body diagrams. Was that enough time? If not, go ahead and pause the video. Otherwise, let's keep going. Okay, so when we're looking at this bowling ball and its first drop, bowling ball is pretty darn heavy. So we're going to say, hey, bowling ball, there you are. And when it's first dropped off the mountain, we have this going on. Force of gravity. So when we're talking about what's the sum of the forces acting on the ball when it's first dropped, we've got this main force of gravity that's dropped. And if we want to calculate that force of gravity, we could look at this and be like, okay, we have F equals ma. So we know that this happens to be our acceleration due to gravity. So our mass is 8.5. And we're going in a negative 9.8 meters per second squared acceleration. So that ends up with a force of gravity of negative 83 newtons if I use sig figs. There might be a little bit of air resistance that's combating the bowling ball, but not a whole lot. So this is in our first scenario. In our second scenario, it's reached terminal velocity, which means that it's no longer accelerating, which means that our net forces are equal. So the force of gravity at this point is equal to the force of the air resistance. So these forces are equal and opposite, which means that there is no net force. If there is no net force, then the object in motion stays in motion. So this object is still dropping, like it's still falling from the sky. It's just not accelerating or changing direction. It just keeps moving in the same direction that it was going in before. Third example. A force of 5.0 newtons to the left is applied to a 1.35 kilogram book. A frictional force of 2.0 newtons acts to the right. What's the acceleration of the book? For this one, you're definitely going to need to do a force body diagram. So take a second and do that. Okay, force body diagram, here I come. All right, I have a force of 5.0 newtons to the left. And since we're talking left, I'm going to put a negative there because we are going in a direction that we generally designate as negative to not confuse our other direction. So it's applied to a book, and this book has a mass of 1.35 kilograms. Okay, and we have a frictional force of 2 newtons acting to the right, so I'm going to leave that one positive. So what is the acceleration of the book? So for my givens, the first thing that I want to do is I want to calculate my net force. So I'm going to add my vectors together. So I have a -5 plus a 2, which would equal a -3.0 newtons. So that means that my net force is going to be 3 newtons to the left. Okay, and if I want to, I can redraw this just so you guys can see. This would be 3.0 newtons is my net force in this direction. Okay, so that's my net force. We calculated that. I also have my mass equals 1.35 kilograms. So now what I need to do is come up with my find, which is acceleration, my equation, F equals ma, and going ahead and solving this, -3 equals 1.35 times a. So when I solve this, I get a equals -2.2 meters per second squared. What does that mean? That means that my book was going 2.2 meters per second squared to the left. Okay, and that's my acceleration of my book. Last example, example number 4. A force of 5.0 newtons to the left causes a 1.35 kilogram book to have a net acceleration of 0.76 meters per second squared to the left. What's the frictional force on this book? So now we're going to have to calculate the frictional force. Again, this is going to require that you draw a force body diagram. Okay, force body diagram, here we come. So we have this way, 5.0 newtons, and I'm going to designate it as a negative so that I don't confuse my vectors. And then I have a frictional force that is, I have no idea. Okay, so that's basically my force body diagram. I have some givens in this particular situation. I know that my book has a mass of 1.35 kilograms, and I know that my acceleration is to the left. So I'm going to designate that with a negative sign and say that it's -0.76 meters per second squared. So I know it's heading in the direction of this force right here. Okay, so I have that and I have that. What do I need to do now? Well, I need to figure out what my net force is. So really what I'm trying to find is my net force. And my equation is going to be net force equals mass times acceleration. Okay, so solving for that, my net force equals 1.35 times -0.76. So with significant figures, that would be -1.0 newtons for my net force. Okay, that's not really my frictional force though. I want to know what this frictional force is here. So how do I solve that? Well, I know that my sum, my net force, is the sum of my vectors. So one vector is 0.5 newtons, and the other is I don't know, which I'll call x. Or if you probably want to do it the correct way, we could say force of friction. Okay, and I can substitute in this, so I know that this is negative 1.0 newtons. So basically, it's the frictional force is 4 newtons when I do the algebra. And because it's positive, that means I know it's to the right. Yay, that wasn't so bad, was it? Happy Halloween, ladies, from David S. Pumpkins.